Following on from last week's introduction to water, what we want to look at today is more on the treatment processes of water. For this week, I'm going to give you these notes as well as a couple of additional handouts that are already on the Ulwazi site. I need you to go through those just to have an understanding of what they're about, but I won't ask specifics in terms of numbers and calculations. So anything that you find here or in the textbook on the sections I've asked, I won't ask you number type questions, but I will ask understanding type questions. For the objectives of this week's lecture, what we want to do is to just introduce some of the types of water treatments that we have around. So you're going to get various different unit operations and things that you can put in different orders. We'll have a brief look at that. In terms of an engineered solution, that's the middle point that we've got there. You can also get some natural treatment systems, which we'll very briefly touch on, and we won't actually concentrate too hard on that one in this lecture, the first bullet point in this slide. And then we'll also look at some sludge management techniques. So obviously when we're treating water, you have impurities in the water, and when you're trying to clean the water out, you need to take the solids away or out of the liquid. So it's not just only treating the wastewater, but it's also to introduce the sludge management process. So water treatment, why do we need water purification? Now, obviously, there is the need for drinking water. So there's going to be one aspect of this where we want to have clean water for drinking, but the other need for water purification is when we have waste management. So waste management, we are going, so liquid waste, water management, should I rather call it. Wastewater management is either going to be municipal wastewater that we need to treat, or it's going to be industrial wastewaters. So municipal wastewater is anything that we flush down the toilet, we go down the sink, the showers, the baths. Industrial wastewater and the purification that we need for is going to be more oils, it could be fats and things from abattoirs, or it could be other things, there's benzene, toluenes that come out of or petrol refineries and things like that. However, when we look at purification, coming back to the slide now, what we've got in front of us, what we want, as we say, is we want the treatment of used water prior to discharge. That's going to be the main focus of the lecture today. So it's prior to discharge after we've made it dirty in some way. You're also going to get natural water pollutants in some water systems. So those could either be from the soil or air. They could be things that leach out from the soil itself. They could be organics, so dead organisms on that slide there refers to both plants and animals. So they're going to be a lot of insoluble organics coming from algae and water-based plants, as well as things that are outside of the plants. You also get things such as soluble organics, so tannins in the Western Cape rivers are quite a big issue, mainly due to, well, not mainly due to, but one of the examples of the tannins is because of the grape industry. So we've already said from the first one, there are natural water systems which could be engineered to treat water, but there are also more engineering solutions that we will look at today. Before we get into that, just some definitions, and I think we should add these onto our list of definitions that's starting to grow under the first module on the Ulwazi page. So basically we have percolation, which is movement of water through the soil. The zone of aeration is the soil where the spaces contain water and air. Saturation, the pores no longer contain any air, it's simply groundwater. An aquifer is a groundwater zone with substantial water trapped between two zones, and we'll get to a picture of that now. An artesian well is an aquifer, so it's that point above, but it's under pressure. Porosity is going to refer to the volume of the void space between soil grains. So obviously if you put sand in a beaker, you can see it just by looking at it that there are air bubbles in between that. And then permeability is the property of the material that allows water to pass through. So how easily can water pass through the system that we are looking at? So when we look at water, or groundwater rather, we have different levels of groundwater, or different sections of groundwater. So at the top here, we have the recharge area, and let me just put the pointer on quickly. So we have the recharge area, so anything that flows into this, onto this land here is going to fall into this soil, and depending on how far down it is, we can have different times that it will take to regenerate it. So typically in this first layer at the water table, that is where water gets pumped out of, and it'll take days after a few good rainfall events to happen for the water to recharge at this level. The deeper we go, if we start taking this well further and further down to pull the water out from here, and if we take all of this water out, it's going to take years, centuries, and millennia for all of this water to get replenished again. If we are now polluting this water, If we're polluting to obviously the same level now as the days, if there's something that comes into that level at roughly that height, if we want to pump it out to treat it, it'll take days to fix this. And again, years, years, centuries, or millennia as it goes down. So the more you pollute, the longer it will take for this groundwater to then get cleared. So this natural treatment, this natural purification treatment can just simply be a matter of leaving something over time. And the natural degradation processes can help, or microorganisms in that water or in the soil, in the natural environment will take care of that natural water treatment. So as we say on the slide, it's a self-purification mechanism. It can possibly purify itself just because of its natural habitat and the organisms that live there. It's obviously dependent on various characteristics. So the first one being how far down did we pollute the groundwater? Has it gone far down? Or as in this diagram, we've only still polluted the water on the surface. So depending on the volume that we need to treat, the turbulence, the characteristics, either the bank or the bottom of the material of a river or something else, as well as variations in sunlight temperature and chemical components, it can be possible to just have a natural water treatment system depending on all of those conditions. There can also be physical processes that can help to treat water, and the first one here we've got is dilution. So dilution, and I'm going to jump straight to the bottom one. We said in our first TUT that dilution is the solution to pollution. It was common in the past, but it is no longer acceptable. So the physical process of actually cleaning a system was simply dilution. So we know it exists, but we're going to cross it out. We're not going to ever physically or actually use dilution. The other physical processes for water treatment can be sedimentation or resuspension. So if there are solid particles in the water, they will settle out and we can remove those and thereby clean the water. If we want to speed up the process, we don't trust the sedimentation process, we can filter it. We can have gas processes, or we can simply have some sort of heat processes. The dilution, as we say, if there's a high concentration around the source, you could then dilute it by adding in a second stream. But again, it's no longer acceptable in most practices. If we have a little bit of a closer look at sedimentation and resuspension, sedimentation is going to involve solids. So it could be either inorganic, organic, or live organisms that are present in the water, and these are now polluting your water stream. Because the solids can vary in size, we have colloidal particles, which are small to large, settleable in inverted commas particles. So theoretically, anything is settleable. It's just a matter of how long are you willing to wait for these particles to settle. So these solids result in an increased turbidity, and they can lead to decreased visibility. So that's the first problem. So it could just make the water look dirty, but as well, it also leads to subsequently affecting the photosynthesis. So if this is in a river, if you are increasing the solid content, the plants are now going to, or the algae, whatever is in the water is going to battle to photosynthesize. This in turn can also interfere with feeding of with aquatic plants. And if they are settling in a slow-moving sections, you can lead to anaerobic conditions, as we've discussed before, and you'll have the silt buildup on the bottom of the water. On the bottom of a river, for example. If we're looking at filtration and gas dissolution, we'll start with filtration. So I think most of you should be well aware of what filtration is. It can, however, also happen in a natural wetland system. So if we have a constructed wetland rather, with a lot of plants in it, their leaves, their roots, their different other things, and as the water flows through these systems, this natural wetland system can act as a filtration. So the debris, as we've got there, can get caught in the reeds, in the roots, and various other plant materials, so it can form a natural filtration system. Gas dissolution, the dissolution of gas in water, is mainly affected by the degree of agitation of water and air. So if you have a higher agitation, you have more dissolution of the gases out of water and back into the air. Gas dissolution, and as I've already said here, I'm giving you the equation, but I'm not going to ask you a numbers question in this course, either in the test or the exams, but we would relate the gas dissolution to Henry's law. Henry's law you've probably dealt with in chemistry, and you're probably dealing with it in some of your other third-year courses. So now that you know where we can use it, some of the examples that you get in your other courses might be on environmental engineering. When we look at heat transfer, so heat is actually also a pollutant to the water. So if we are going to discard hot water from your industrial process into a river, it is seen as a pollutant. So that hot water, so water bodies are then going to heat up or cool down depending on what water it is that you are adding. And because of that change, while aquatic animals have developed some tolerance to it, they have not developed mechanisms to deal with abrupt changes in the temperature. So animals obviously are able to adapt over summer and winter, but if you're now adding 4 degrees, let's just say example, 4 degrees Celsius change, sorry, I'm just seeing that number there, you're probably going to kill some of your wildlife that's in there. Okay. So the other thing that it does with the heat transfer is that different waters are also going to have different densities. So coming back to at 4 degrees Celsius, that's something totally different, not what I was speaking about before. It has a maximum density at 4 degrees Celsius. Okay, so the density changes as water moves towards freezing point or as it grows warmer. So there's a dual effect on that. Okay, and I'll let you read through the rest of the slides for heat transfer. We can also have chemical processes. So these are fairly complex, but we are in a degree where we've done a lot of chemistry. So redox or dissolution precipitation actions can happen. Water and carbon dioxide, or the other reactions, there are various things can happen in the water to affect the pollution, either to purify the water or to get it dirtier, I suppose would be the word. So now if we look at a biological process, so biological process as natural water purification systems, and looking at the slide, let's just start at the top in the middle here. So we've already said that dead organics are going to be a pollutant to water. So biochemical processes rather can convert these dead organics through an anaerobic system, so anaerobic nitrogen, carbon, and sulfur cycles. So there we have NC and S. So these dead organics can become the initial product for biochemical processes where it's converted to CO2 and H2S. These intermediate products, so we can then also get ammonia, carbon dioxide, and various sulfides, become part of a final stabilized product that gets taken up by plant life. These plant life obviously then can die. Oxygen and proteins, animals, it's no longer plant life. Animals then breathe in the oxygen. Proteins and fats and metabolic processes from the plant life excrete CO2, and we come back to a system of having nitrogen, carbon, and sulfur material from dead organics. And this can go in a circular motion through biochemical processes to help purify water through natural processes. When we look at a more traditional engineering type approach on a water treatment system, you're going to see things that look a little bit like this on the right. There are large cement tanks in most of the industrial water purification systems that are linked together from one section to another doing various tasks. So the first one of this is going to often be screening and grit removal. So let's remember that everything that you flush down the toilet, everything that gets through the wastewater system is going to end up at this wastewater treatment plant. So any of your cigarette butts and any other solids that get flushed down the system are going to have to be removed through screening and grit removal. The typical process that then follows, and I've asked you a TUT question on this so you can read up a little bit more in the textbook or online, is going to have various different sets of these that we've got here. So typically there will be a primary sedimentation. So simply like that diagram on the right, water will enter and the solids will settle out. So water is being entered. You can't see it in this diagram here, but on the right-hand side you can see one of these empty ones. Water will come up through the middle here and get the solids, and the liquids will come in through the system. So you can see it just hiding behind there. Water will come in here, flows over, the solids settle to the bottom. So at the bottom there's a solids removal system. As this flows in, water will flow over this top section here. So there might be an initial amount of solids coming over here as well. There will be a second set or second opportunity for solids to then settle out again. Again, they're going through the bottom, and you can see on the edge here, the water is trickling over the top here as a primary settling tank, or this actually might be a secondary one. The water looks fairly clean. Okay, so that is a primary settling tank for clarification. You might get further ones, and we'll get through to these later on later slides. We might want some mixing and coagulation, so some particles might stick together and coagulate more better if there's agitation. If we add chemicals, you'll get some flocculation and further settling out. Secondary settling will be exactly the same thing as I've just described with the diagram on the right, except we do it a second time round. You might have filtration, sludge processing, and often the last step is going to be disinfecting, which is typically done with chlorine, some chlorine gas, just to kill off any of the last microorganisms that still exist in that system. While I'm just looking at this and going through this again, screening and grit removal. So we've just said anything that you throw down the toilets and things like that are going to end up at the wastewater treatment facility. In most of the systems in South Africa, there are two different water processing routes. So the first one is the municipal sewage system. So anything that you flush down in a house, either flush down the toilet, the shower, the bath, sinks, basins from a kitchen or a bathroom or anywhere else, goes into a system of pipes that then flows through to this wastewater treatment system. The second one is the stormwater drain, and a lot of people get confused and think that the stormwater drain comes to the same system. The stormwater drain is the thing that's in the streets. So anything that you see on the street, there's a little opening in the streets, then the water can flow down when it floods. That system does not go to a wastewater treatment system, it goes straight into our rivers. So when you see people throwing things into the streets and then it gets washed into those systems, it's not ever going to get collected, it's going straight into our rivers. Okay, so those are the two different systems. The stormwater drains, which we are not dealing with today, and the municipal sewage works, which is what we're showing on this slide and from now on. So once we've had that very brief introduction on what a wastewater treatment system does, what we are aiming for is to have certain wastewater quality standards. So wastewater is going to come in, so polluted wastewater that we then need to treat. And when we send that that treated wastewater back out into, often it's the rivers, sometimes it's the sea, it needs to conform to these general limits. Okay, maybe not the general limits, the special limits. So this is coming from one of the standards. So I've put the standard on the Ulwazi page as well, so you can go and see the whole thing. I've cut some of the bottom off here because it doesn't quite fit onto the slide. Excuse me. But here are the limits. So if you have water that's coming out of your wastewater treatment plant, you cannot have, let's say, for example, water outside of the 5.5 to 9.5 limit going into your rivers. So most wastewater treatment facilities will have that final disinfectants section. It will then go into some sort of maturation pond, so it's basically just a big open lake or river sort of system, which then ultimately feeds into another river or into the proper river or into the sea. So this water isn't coming back for consumption for us to drink, it's going back into the environment. And any wastewater that's going into the environment must adhere to these standards here. You'll see that there is a general limit. So the first one is just the only example I'm going to use now is 1,000 fecal coliforms per 100 moles, whereas the special limit is 0. One of your TUT questions, I've asked you to tell me what is the difference between the general limit and the special limit, and why are they actually different? Okay, so yeah, I could have zoomed in earlier there, but as I say, I've cut off the bottom of this. It is on the site, the Ulwazi site for the whole document, so please go and have a look at that. Okay. The drinking quality standard, and I've also put this one up on the Ulwazi site, so please go and have a look at this as well. This is SANS 241 of 2006, and this is giving a similar document in terms of what you're allowed to have in terms of drinking water. So if we try and compare these two, we have pH, conductivity, and I'm trying to see we had and unfortunately I can't flick back to the slides now to go and see what was on the previous slide while I'm recording. So have a look for yourself and see how are these limits different on what is acceptable as drinking water versus what is acceptable to send out into our rivers. And why do you think these two are different? Why are they not the same? Sorry, there we go. There's the coliforms, E. coli coliforms count. It's on 10 and it's on 0. So the previous limit was 1,000. This is now either 10 or 0, depending on what we are looking at here. So what is the difference between these, and why is this one so much lower than for the municipal wastewater that we looked at earlier? Okay. So from that document that you've just looked at, and I'm going to ask you to refer back to that the whole time because I can't look at it as closely because I'm trying to record this and can't have multiple screens going. There are various different things that are talked about. One of them is hardness, and hardness in water is something that is often not a desirable, but it's not the worst thing in the world. We still have our standards, so please go and just double check what that standard was. As I say, I don't have it in front of me. What exactly is that hardness in water though? It is something that is caused by multivalent cations or minerals, particularly calcium, magnesium, and iron. So hardness in water relates to how much calcium, magnesium, or iron is in water. An easy way to see the hardness of water is when you are in the shower or when you're trying to bath or wash your hands. If you've got a bar soap and you're trying to make that soap, you're rubbing it between your hands with water. If that soap doesn't want to make bubbles or sort of rub off the soap, it's difficult to do that. That's often a sign of hard water. What that hard water comes from is it's dissolving the rocks or soil or rocks in water. So wherever this water came from, it's been dissolving that water. So it's not necessarily a pollutant that is due to what you and I do in the house, but it's from where the water originally comes with. Okay. In terms of a typical plant to treat hard water, so this is more on the drinking water side and not necessarily on the wastewater treatment side. Typically, you will have raw water coming in, flocculation, precipitation. There are then softening agents that you can add. So we add different chemicals, the calciums and the sodiums. What that does is it can then remove the Ca2+ and the magnesium 2+, which cause the hardness, and you can then come out as instead of CaOH2, you've got CaCO3. Okay. We then filter it just to make sure that the chemicals come out, disinfect, as we said, with chlorine, and then you can obviously, the storage isn't really a storage, it's let's send that water out for drinking. Okay, so this is for treating hard water, which, as I said, is typically from a groundwater process and not as common in industrial. Well, it could be in an industrial setting, industrial wastewater, but not that common in a municipal wastewater system. The common water treatment plant, so this is, if it's just general water, I'm going to leave that one for you to look at. You've got the slides, you can pause, you can have a look through that one. Other typical wastewater treatment units are going to be for the coagulation and flocculation for water treatment. So you might have a reservoir. Oh, sorry, I'm seeing multiple dots on my screen. I hope you're only seeing one. So there's a reservoir. You have coagulant, which can get then added. The flocculation tank, we can then mix the chemical that you added, the coagulant that you added. If you mix these up, the small flocks then grow inside to flocculate out, and we can then collect the sludge as it's coming out. We will always filter in case the sedimentation basin isn't taking out all the sludge. We can disinfect again, and then you've got water coming through. The sludge, we can have various different uses for that afterwards. In this example, we're looking at it in terms of sending it off to land. Sorry, not landfill, it's called landfill there, but it's for using it in to help grow trees, I suppose, is the best way to describe it there. Okay, so there are also examples of how to treat water, a typical plant for turbid water. So we again have the raw water coming out, and there are various other things. Again, please stop and have a look to see how you would treat turbid water. Most processes that we've had so far are more on treating clean water. So sorry about that, the slides in this are a little bit misleading. So you can use those for treating wastewater, but some of those are more specifically for if you have a particular type of groundwater that you're trying to clean out. There are industrial wastewaters as well that might be turbid or hard or various other things, so you would also use a similar way. From now on, we're looking more at a traditional wastewater treatment facility. Okay, so as we already said, wastewater treatment, it's either going to be industrial, so that can come from any industrial site, so even mines would often have their own wastewater system on site. Any water that they've got on site from a mine, it could include anything from the ablutions as well as the kitchen areas, but also any of the water that runs off, so it might have a lot of oil in it from the machinery, things like that, and any other industry that you can find, as well as anything from domestic activities. So the domestic activities is going to be the municipal wastewater that is in our area. These are the things that we are wanting to look at now. So obviously the objective of the wastewater treatment is to reduce the number of pollutants to that level, and that level is per the document that we had earlier on, those standards for the wastewater into the environment, if that's how we're going to be doing it. Okay. Typically, there's going to be a series of reactors and units. There is some recycle in some of these instances, and we'll get to that in a bit, I hope. Okay, so these sites, these wastewater treatment facilities, this is what a typical municipal wastewater site looks like, and it takes up a fair bit of space. So often we have sent our fourth years to go and look at a wastewater treatment site because it's actually quite easy to get students onto. There's nothing really dangerous on here to get you hurt, so Sassels and those places are fairly difficult to get you onto these days. This, of course, is pre-COVID days. The other thing you'll, as I say, already mentioned, the size of this. So the size is often quite big in these municipal wastewater treatment plants. So I'm looked at this earlier and I was sort of battling to make my way around most of these things. So it's not in a linear fashion. The waters flow linearly, but it's not necessarily in a linear fashion. The water will come in at the grid screen, from what I can see on this diagram. So there isn't a flow chart on this, so I'm making my best guess is the way I think it works. It will come into the grid screen as our previous one, flow into this primary settling basin. So there we can remove most of the solids. There typically isn't a chlorine contact chamber, and this is where I'm getting confused because this is probably the last step. So it probably comes into this thing, it needs to come out somewhere else. And the next logical thing that would be to come into these secondary clarifiers. Okay, so the one's not working here, these others are. From these, we're going to have solids that are going to go into this thickener unit here. So that's where the solids are going to come into the thickener, then onto the fermenter for the last stage of purification or sort of treatment of the solids. So that's where these secondary clarifiers send the solids. It's then going to take the liquid and send it through to the bioreactor. Okay, now this is again where I'm getting confused because sometimes the bioreactor comes before the secondary clarifier. Okay, but I'm not quite sure, or unless it comes from the primary settler around here to the secondary clarifier and back to the chlorine contact chamber. So the last step will be this chlorine contact chamber, and from there, I'm not sure what that is, but that could very well be a pipe that then sends this out into the river on the system. I don't think this is a South African system because most of our rivers are not this big. Okay. There's also a digester here, so that will be for solids. So there'll be a thickener here, the fermenter here, and then followed by the digester. There's probably solids coming in here as well. The primary settling basin I'm not quite sure where the solids are going in terms of this plant as we've got in front of us. Okay. So categories for industrial wastewater treatment, and I've used the word industrial wastewater treatment here, but the word municipal could fit in here equally as easily. Typical steps are going to be physical separation. So we've already said there's sedimentation, clarification, and flotation. There's going to be a biological step, and often this is a secondary treatment. So sometimes there's also a physical secondary step, but more commonly it's a biological step. And this is going to be both aerobic as well as anaerobic. So aerobic is going to be on a suspended growth process. It could be a fixed film process or an aeration lagoon. So these are ors in here on how the aerobic system might work. Some might have multiples, but generally it's an or. Physical primary, biological secondary, and then the third process, the tertiary process, is going to be a chemical system most probably. I've already said there's a chlorine. So that's a coagulation, precipitation, flocculation, neutralization. The neutralization step is often a tertiary step, that last step. Some textbooks you will see, they're going to talk about a finishing step or a polishing step. So it's not going to be 1, 2, 3 steps. It's going to be 1, 2, 3, and a 4. That final polishing step is if there is a natural wetland system which the water can go into, or a semi-natural wetland system that it can go into, where there's some natural processes before it goes into the actual river or the sea. Okay, so wastewater treatment plant, here's one of the pictures of it. There are various others. If you Google it, this is probably not the best or the most logical one because there are some steps missing. But as we said, there's the preliminary treatment. There's going to be a screen which is going to remove some of the solids that shouldn't be in the water in the first place, the equalization tanks, secondary screening tanks, and then we follow with the biological treatment. There may be membrane tanks even, which haven't been mentioned before, which then go through to disinfection. In this one, blue arrows are representing water, and these brown ones are representing the solid waste. So you can see most of this is linear. So the water in this instance is linear. There is, however, a return biological sludge, and that's why I've used this diagram, because it's the only one that I could find easily that had this return system on it. So in these systems, these biological tanks, we have microorganisms in here that are going to be reacting with the water with the sludge to neutralize them, either in an aerobic or an anaerobic system. Those microorganisms we don't want to just send straight out into both the solid stream or into the water stream. Well, actually, the microorganisms we don't want in the water stream, we only want them in the solid stream. But because those organisms are now used to the systems and they have grown acclimatized to what's going on here, they then get some of them get sent back for a recycle. So those healthy microorganisms can get sent and do their jobs. That's why there's this recycle happening here. In terms of primary treatments techniques, if we just go back and have a little bit more time to discuss what those are. So the first primary technique, we've already said, is the screening. So screening is to remove all the cigarette butts and anything that you've thrown down the toilets that you shouldn't have thrown down in the first place. And that literally is just a grate. So it's a piece of metal with holes in it that let the water and some of the smaller solids through that will be treated. But any other piece of plastic, and there's some very funny things that you see if you ever go there. It's golf balls and other, who knows what you can find in those things. That will be taken out of screen, and that goes straight to a landfill. After that, this water and any of the solids that are left, so this will be fecal matter that's going through here, are going to go through various primary treatment techniques. Mainly, it's used by gravity. So gravity is going to remove a lot of this material. So in this instance, gravity typically removes 1/3 of the biological oxygen demand, and it can also remove 1/3 of the suspended solids. So SS in this instance is the suspended solids. So it's typically modeled as a plug flow reactor to minimize the turbulence, and it has a low velocity. So a settling tank, we don't want a settling tank to be highly agitated, so there's not going to be any aeration in this. We don't want bubbles pushing the solid particles back up. We want this to flow nice and slowly so that the particles can settle. So that's the sludge. They can have, where the flocks are formed. So if you added a flocculant or anything else to make the flocks form, those are typically the aluminum hydroxides, CaCO3, clays, which are not highly biodegradable. We want those all to settle out. We do then separate the solids from the liquids. So how big do we need this primary settling tank to be? It all depends on the size of the materials that you've got in here. So if we have a particle diameter of 10 millimeters, so that's roughly, in this size, they're calling it a pebble. That's a small pebble in my mind. The settling velocity is 0.73 meters per second. So you can have fairly small, so if we think of it in terms of a swimming pool, at the swimming pool with the water coming in on the one side and going out on the other side, it doesn't need to be a very long swimming pool for all the pebbles to have settled down if we're flowing it from the left-hand side to the right-hand side. As you get smaller though, so we now go by a factor of 10. So we've got a coarse sand, fine sand, silt, large colloids and small colloids. The times go from meters per second, meters per minute, meters per day to years. So if you have a silt, so these are fairly fine particles here, there is almost no way that you can design a settling tank to separate out a silt at this speed. So this is a simple settling speed. So I've already discussed this with you. I'm not going to be asking you to calculate the settling velocities or how big does your equipment have to be in order to settle out the required numbers. Some of you have probably already seen the maths to this calculation for settling tanks. By the end of your degree, all of you would have seen these calculations. Okay, so you will see in fourth year there's SFS, and I'm not quite sure what if it's got another name for the METs. You'll both see a course where you calculate these for sedimentation, these settling velocities. If you want to increase these settling velocities, what you do is you add artificial gravity, and to do that you spin things out. So if we wanted silt to settle out faster, we'd add it to a centrifuge or a hydrocyclone or something like that, and those particles would settle out faster. In systems like we have here, we will not typically use a centrifuge or forced settling because of the volumes of water. So particularly with the municipal settling, if you had to send everything through a centrifuge, you are going to be using a lot of energy. It's easier to have, and as we said previously, those big spaces and just have the particles settling out over days. So 8.6 days is still a fairly long time, but it probably is manageable in some of these systems. I've heard of wastewater treatment plants that are typically, they say, residence time of about 2 weeks. Okay, so 2 weeks, or up to 2 weeks, I should rather say. So if we have a settling time of 8.6 days, it is possible that some of the silt will settle out, but the colloids, when we're talking about years, you're not going to be separating any of those out. If we wanted to separate those out, we would probably add a filter. Again, because of the volumes of water in the municipal systems, adding a filter is going to clog up fairly quickly, and then you have the problem of changing the filter. Okay. If we want to make those particles bigger, though, the one option is to have coagulation and flocculation. So we've already seen a diagram of this before. So if we have the turbidity from those tiny silt particles that's in our wastewater, we can then add some coagulants. So it's a polymer calcium hydroxide or ferric chloride, which we add to the water to neutralize the charge of those particles. And then what happens is because of the charge change on that, these individual particles then stick together in a flock, and that flock becomes heavier and bigger, and as we saw from the previous slide, the bigger something is, the faster it will settle. So coagulation is a chemical alteration of the particles to make them stick. Flocculation is when that particle then grows. Okay, so it may require some different velocities to encourage the particles to come together. Once they are together though and they are bigger, they can then settle out more easily, or they can filter out more easily. The filtration, that's the next one that we've got here. So there are various different filtration options that are needed in wastewater treatment, particularly the municipal side. It's not as common as maybe industrial or some of the smaller ones, simply because how do you then clean that filtration system afterwards? So some methods are using a sand filter, so you can use that one quite easily. Sand is rather cheap and it's quick and easy to just replace the sand as the filter gets clogged. It can also remove the pathogens as well as other small particles. If we had to have a filter with activated carbon, you can also have removal of some organic matter. But as per the last point, which we already said a few times, it's going to require cleaning, which is not always that easy. In terms of biological treatment techniques, which listed here are as secondary, what this is going to do is convert most of any of that remaining soluble or colloidal organics into a more settleable microbial solid. So this can either be aerobic or anaerobic, but what both mean is that the microorganisms or those microbes grow and reproduce feeding off that organic matter. So any organic matter that is left over, they can then feed on that. That microbial mass, so as you've got these microorganisms growing, that is then removed in that second sedimentation process. So we then have a second degree sludge. There's going to be two different types, or there are possibly two different types of microbial treatment. The first one is biofilm growth, where the microorganisms grow on the surface over which the wastewater flows. So this is a trickling filter, and we'll see a picture of that now, or as a packed column. So water literally filters over a slimy layer, which is that biofilm, or we have suspended growth, where the microorganisms are in the water themselves. So wherever the water goes, the microorganisms are in the water as well, as part of that activated sludge. The activated sludge meaning that there are microorganisms with the water. So here we have an example of an aerated tank. So this is the municipal wastewater, or actually it could be industrial as well, where there's water coming in the one side and there's an aeration happening here. So the aeration treatment here is to encourage the microorganisms to grow through an aerobic process. And the more microorganisms you get through that aerobic process, the more of the pollutants they are going to eat, more of that organic matter they are going to eat. And sorry, I see there are a couple of spelling mistakes in the slide. So those aeration tanks, just looking at it slightly differently, so we will have air coming. So this is a terrible picture quality rather. So there's a pipe at the bottom of this tank, like we've got in the top and in the previous slide. There's this pipe at the bottom where we force air through it. It then bubbles up through here, which allows for mixing as well as for the microorganisms represented here as little green Pac-Man type things, which then eat the organic matter. They can then eat any of that organic matter to remove the pollutants, and then it's easier to remove the microorganisms later. Okay. In terms of what are the treatment techniques, the advantage of this is that it's low cost and it's fairly simple. So if you've got the system going, you can simply just let it run and nothing needs to get added. You're not adding any chemicals to it. You're not taking any chemicals out. The microorganisms are the little mini factories on their cells, and they can do it at low cost and it's simple. Unfortunately, some of the disadvantages means that it's less effective for highly toxic compounds. So where we would need some chemicals to try and neutralize it, it's less effective than those. And because of the speed at which the microorganisms can operate, they can often take up large spaces. So we talk about lagoons here, so they're very big systems. There are various systems that we can do. Typically, they're biofilters or trickling bed, which we've mentioned already. Activated sludge was per the slide that we had before. And then they're also rotating biocontactors, which I don't think I've ever seen in person, or a fluidized bed reactor, which I know some of you or most of you have probably seen in your third year prac course, where the fluidized bed has the bioparticles already attached to that system. So just looking at some pictures of this very quickly. So the trickling bed filter system, so we can see there's some sort of rocky bed on this diagram at the bottom right. So I'm not quite sure where this rocky bed forms in the top here. These look a little bit like plants. But either way, there's some solid bed that happens here, and the microorganisms are sitting all on these little pieces of stone. So they attach themselves to these beds. The dirty water, the polluted water, then gets trickled over. So this is a fine spray on this arm here. This arm is then rotating around and around. The water falls on there, flows down through here to collect through the groundwater, and the microorganisms can then do their thing on the rock. As you can see from the water that's going out here, or as you can hopefully imagine, the water coming out here is fairly slow. So if you want to have this sort of system, you can't have large municipal wastewater treatment systems with large volumes of water, as we saw in some of the other diagrams. So that we say is that there's a trickling bed filter. So what happens with that is that there's a degradation of the organic load. So typically you are then going to have a CH4 and a CO2 coming off that. So that is the product of the microbial systems. The CO2 is often vented off into the atmosphere. The CH4 in some more complex systems will actually get collected so that you can use that as a gas. This often also works in digestion tanks. So this is now not the liquid stream, but this has now been separated into the solids. So the solids can also undergo a digestion through microorganisms so that we can break that down to make them more environmentally friendly, I suppose. The problem with a lot of these systems, when we talk about anaerobic, and it's something that we should have had on the previous thing, it can be very temperature sensitive. And the reason for it to be expensive, as per the diagram below, is that it's expensive per unit of water. So if we have a simple aerated tank from the 2 slides back, where we had the little green Pac-Man, the little green Pac-Man system can have a lot of water at once, whereas these trickling bed systems, you don't have as much water trickling through it as those ones do. If we're looking finally now at the chemical, physiochemical systems on the tertiary systems, some examples include ion exchange. So ion exchange, we can either have a synthetic resin, we can have a zeolite, or we can have activated carbon. So these have different functions in order to treat different waters as the last step in the water treatment. It's not the solid section, it's just the water. There's also a step which could be a stabilization step or recarbonation where lime is added. So that's added as a coagulant as well as to raise the pH. So you want the pH to come up a little bit depending on what the pH is. There are other stabilization steps which might want to reduce the CO2 step. Okay. The last one that we've got here is disinfection on this page. So this is going to destroy any pathogenic organisms. So the water that you got right at the start of the municipal wastewater system might have had various microorganisms that come in that are not wanted. We don't want to kill those microorganisms at the start of the process, because if we kill those bad bacteria, we're also going to kill the good bacteria that are going to be used in the aerobic and anaerobic digestion steps. So we're going to rather kill those pathogens right at the end before this water goes out, either into the river, the sea, or for other uses. Okay. The thing with this is we need to balance the contact time and the concentration of the disinfection, because if we put too much chlorine into this, we are then sending chlorine out into the streams and rivers, which can then again kill or harm any of the wildlife or the plants, animals out in the rivers. So chlorination, I know I've said disinfection there, but sometimes it's set out as 2 different steps. So chlorination, there's some additional steps on chlorination here, which I've actually technically discussed in some of them in the previous slide already. So I'll let you pause and read the slide. There are also some alternatives to simple chlorine disinfection. A lot of them, though, you will see include the word chlor. So they are chloride dioxides. So it's still a chlorine step, but not chlorine gas Cl2. 2 other steps where we might have disinfection alternatives is ozone. So ozone I have seen being used in both municipal wastewater systems as well as industrial. So you can, particularly if you have abundance of oxygen, and this needs to be pure oxygen, not air, although air will work. So you can produce ozone through a quick and easy little process, and then you can put that into your water. The thing is, it is expensive, which is a bad thing. It degrades rapidly, which is potentially a good thing. So it does its job and then it's out of the way. But, or good or bad, it must be produced on site. So you have to have your own on-site ozone production facility. Another one is UV. So this is technically a non-chemical method where you can pass light over the water, and UV at certain wavelengths, and seems like some words are missing there, UV at certain wavelengths will kill pathogens in the water. So they will again kill microorganisms in the water. Once we've done all of this, so we've now cleaned the water through primary, secondary, and tertiary treatment. As I said, that water then, what do you then do with that effluent disposal? So typically that water will go into a river. So I know in the Gauteng region, most of that water that's then treated is to acceptable standards by the standard as we had in the previous thing. So it is fairly clean and it can go into rivers. The same thing, it can go into dams. And sometimes, if you're at the coast, it goes into pipelines, which then get discharged out into the sea. There are different standards for rivers versus the sea, and I've also added that document for what is the water standards that you can discharge into the sea. So the sea is much bigger than a river. So technically, if we were abiding by the dilution factor, the dilution of the sea is going to be much more effective than the dilution of the rivers. But still, dilution is the solution to pollution, is no longer a solution for modern engineers. These are all governed by those permits that we've already discussed earlier, and those are with the government, and that is the respective the respective department as applicable. This is the water that comes out. So this is not the cleanest of water. I should have used a better picture. The water that comes out of these systems is very clear. It looks like you could drink it, but you probably, I know the wastewater treatment sites say you shouldn't drink it. This is the water that comes out of these sites. The secondary pollutant that was sorted out was was the solids. So we now want to look at some of the solids. So in those steps, we are going to take out solids both in the primary treatment as well as some in the secondary treatment. So this is effectively a byproduct of that wastewater treatment. So we are going to have 95% water, and that is including SS, suspended solids, dissolved solids, chemicals, and it's going to be a variable composition. There may be some water in it. I'm not quite sure. Sorry, I can't think why I wrote 95% water here now. So I think it's 95% of this site is water and only 5% is solid. So depending on how good your process is, you're going to have a wet sludge or you might have a slightly drier sludge. So the primary settled sludge is then going to be a thickened material generated from that primary sedimentation tank. So that will then be dewatered further. Sorry, hang on. That 95, sorry, I'm getting myself confused now. That 95% water is how much water is in the solids when it gets to the solid handling. We haven't thickened it yet. After dewatering and thickening from after that, we can get up to 2.2 to 8% solids. So this is still a fairly wet sludge. Okay, so these chemical sludges can then be digested anaerobically. So it's still a very wet sludge. So this digestion is again without oxygen. And as we said, it could be a trickle bed filter, but there are microorganisms that now break down any of the, break down the solid material further. So there we have a digestion tank. The solids will be put into this tank. It will be sealed so that there's no air in it. As we said, it's quite a liquidy sort of thing. This sludge digestion tank, the settled sludge from the primary and secondary clarifiers, is pumped into this and it's obviously digested anaerobically. There are two main steps in this. So first of all, there are going to be complex organics. So the complex organics in this could be fats, and these are going to be converted into simpler organics. There are acid-forming bacteria, which are tolerant. They can be in here for 10 to 15 days to take this step. So that is this first step that we've got here on this step here. And sorry about the quality of this diagram. The second step is then going to be the methane-forming bacteria. So once we've got the complex organics that are broken down, we're then going to have these the more simple organics broken down by methanogens. So methanogens are then going to produce methane, which can then be burnt off on site as an energy producer, and the final effluent, which is our neutralized solid waste, which then we need to dispose of. So in terms of what do we now do with this wastewater sludge management? So we have a very thick, and sometimes can be fairly solid, depending how much water you've taken out of it, sludge that has very few uses, or does it? So most landfill sites will simply take these and put them on a land somewhere. So the land application can be to cover it and then grow vegetables or crops on it. There is unfortunately, or there's some perception about should we be using our fecal sludge and then growing things on top of it. It could actually be, it doesn't have to be for plant or, for human consumption. It could just be for other land applications. The second option, when we say land options, we can simply throw it in a landfill. The amount of solid waste that gets generated, is there enough landfill space to be sending this through? A third option is to incinerate. So the solid, we could be burning it. So this, depending on how far through the sludge handling process it goes, it could still have a fairly high calorific value. So if it has some calorific value, we could burn it, that solid waste, and we could get some energy recovery from that solid waste. Okay. However, this all depends on its source, its geographic location, the community, quantity, quality, quantity, I've repeated that word, sorry, as well as the big one there is the public acceptance and the local conditions. So there are some examples of where it's used as an energy source to make bricks. So you can use it for the energy for bricks, or you just simply throw it away. It all depends on what is available. Okay. As I already said, a lot of this is in the textbook, so please can you go and refer to page 281 to 333 of Masters and Ella. In terms of, again, just to reiterate, whatever you find on page 281 to 333, if it asks you to calculate a number, I will not be asking you to calculate those sort of questions. So have a look at the TUT on what sort of questions I will ask you, and I'll give you more examples as we get close to the TUTs and tests of what sort of questions I'll answer. I will not ask you those questions on the numbers, because that is going to come up again in one of your other courses. So when that time comes, you now have the examples and you know how this might be applied. Okay, thanks.